Okay, guys, welcome back. We have a follow-up question to the previous video from the third chapter of Mechanics of Materials by Johnston, and we have a torque of magnitude 1000 Newton meter that is applied at D, as we can see. And we know that the diameter of the shaft AB is 56 millimeters and that the diameter of the shaft CD is 42 millimeters. And we need to determine the maximum shearing stress in shaft AB and CD. So as we talked about in the previous video, we have the elastic torsion formula where the maximum shearing stress is equal to torque times the radius of the shaft. We can show it with C over J, and our J is 1/2 of pi C to the 4. It's going to be the moment of inertia, and if we just plug that in into our formula, the maximum shearing stress is going to be 2t over pi c cubed. And very simple on this one, we just have to figure out the torque in member CD and AB, and after that it's easy enough to find the maximum shearing stress because we have the information for the radius. We know the diameter is 56 for AB and 42 for CD. So let's start with the CD. As we talked about in the previous video, the internal torque in the shaft CD is going to be the 1000. So let's start with CD. The maximum shearing stress would be 2 TCD over pi C cube. So 2 times 1000 over pi. So the diameter is 42 divided by 2. That's going to be our radius. And since this is in meter, we're going to multiply it by 10 to the minus 3 to get it in meter. And let's see what we get for this. So 2000 over pi times 21 times 10 to the minus 3 and all to the power of 3. So that's going to be in Pascal or 68.7 megapascal for maximum shearing stress for CD. Let's move on to the member AB. And now we need to figure out the torque in member AB. As we talked about in the previous video, if we look at from this side to these two gears, we're going to have something like this, where we have the force in here from each of them, which is perpendicular to the radius of the circle, and these two forces based on the Newton's law are the same. They are basically action and reaction, same magnitude. So the torque that we have for each of this for CD would be F times the R. For the member CD, you can call it RCD, and the torque that we have for member AB is going to be F times R AB. So since these two F's are the same, we can conclude that the TCD over RCD is equal to TAB over RAB, and basically each of them are F. So that's how we're going to figure out the torque in member AB, because we know member AC the torque is 1000, and the torque is in this formula because our F and R are perpendicular to each other. We know from the geometry every tangent on the circle is going to be perpendicular to the radius. So now we have the vertical distance, and our moment or torque would be basically F times R. All right, so if you want to find the T, AB, you basically have TCD times RAB over RCD. So this is going to be 1000, and RAB is 100. This is going to be 40. So that's going to be 25. So, sorry, 2.5. and we're going to get 2500 Newton meter for the torque of AB, and the rest is same as what we did before. For this time AB, we just have different torque. So 2 times 2500 over pi times the C is different because we have a different diameter for this shaft. It's AB is 56, so 56 divided by 2, again times 10 to the minus 3 to get it in meter. And let's see what we get in here. So at the top we have 5000, and here you have 56 divided by 2, or 28. And yeah, that's going to give us 72.5 megapascal and the maximum shearing stress for member AB, or the shaft AB. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.